It's my pleasure to introduce Ashvin Swaminathan from Princeton University, and he's going to speak to us about two Selmer groups, two class groups, and the arithmetic of binary forms.
Thanks so much for the introduction and for the generous invitation to speak. Today I'm going to talk about rings associated to binary forms and how the arithmetic of those rings can be used to study two Selmer groups of hyperelliptic curves and two class groups of number fields. Okay, so here's how the talk is going to go. I'll begin by defining the ring associated to a binary form. So if F is the binary form, we denote the associated ring by RF. And then I'll tell you about a new parametrization for square roots of the ideal class of the inverse different of the ring associated to a binary form. Now, this parametrization has many applications, but a feature of the parametrization is that it depends in a significant way on the leading coefficient of the binary forms under consideration. And so it applies very easily to families of binary forms with fixed leading coefficient. So for such families, we have the following applications. We can compute the average size of the two torsion in the class groups of these rings. And if F is a binary form of odd degree, you can look at the equation z squared equals f of xy. That's known as a superelliptic equation, and one is interested in studying the integral solutions to this equation. And we can use the parametrization to prove that most of these equations have no integral solutions. And an application in the case where f is of even degree is you can look at z squared equals f of xy again, same equation, but this time it defines a hyperelliptic curve. And we can use the parametrization to compute the average size of the two Selmer group of the Jacobian of this hyperelliptic curve. Now, all of these applications actually make sense for families of binary forms with varying leading coefficient too. So it's natural to ask whether we could reproduce these applications for such families. And so far, we're able to do that for binary forms that have small degree. So for example, when we're looking at binary quartic forms F with varying leading coefficient, we can compute the average size of the two Selmer group of the Jacobians of the curves given by z squared equals f of xy under a technical assumption that they're everywhere locally soluble, meaning that they have rational points everywhere locally. And as a consequence of that, we're able to compute the second moment of the size of the two Selmer group of elliptic curves. And a very closely related problem to studying two Selmer groups of elliptic curves is studying two torsion in the class groups of monogenic cubic fields. That is, cubic fields where the ring of integers is generated by one element. And so we're also able to compute the second moment of that. And here on the slide, I've written compute star everywhere. And the reason is that we're not quite able to compute these quantities. What we do is we get upper bounds on these quantities, and we expect that these upper bounds are optimal. Okay. So that's how the talk will go. I'll start by defining the ring associated to a binary form. So for this, we'll fix a base PID R, let K be the fraction field of R. Now let F be a binary form with coefficients in R. The coefficients will be denoted F0 up to Fn, and suppose that it's separable over K. And now let Kf be the K algebra obtained by adjoining a root of F to K. So it's just K join X mod F of X comma 1. And let theta be the image of X in Kf, that is, theta is going to be the root of F. Now, a bit of notation. For each I from 1 up to n minus 1, I'm going to define a polynomial pi in one variable. The coefficients of this polynomial pi are just drawn from the binary form. So it's the sum j goes from 0 up to I minus 1, fj t to the I minus j. And I'm going to let zeta I be what you get when you evaluate pi on this root theta. So zeta I is going to be an element of kf for each I. Then we have the following definition. To the binary form F, there's a naturally associated R submodule, RF, sitting inside KF, and RF is a free R submodule of rank n with basis 1, zeta 2, up to zeta n minus 1. This is just an R submodule right now. This module, RF, has been studied extensively in the literature. So 50 years ago now, Birch and Merriman proved that the discriminant of the binary form F is equal to the discriminant of the module RF. And it turns out that RF is actually a ring and hence an order in the algebra KF. And the multiplication table of this ring is given as follows. So if you take the two basis elements zeta I times zeta j, then their product is a linear combination of the zeta k's, where the coefficients are drawn directly from the binary form. This was proven by Nakagawa in 1989. So this construction might seem a bit arcane, but at least in some cases it should be familiar. So in the case where n equals 3, the assignment taking a binary cubic form to its corresponding cubic ring agrees with the Delaunay-Faddeev correspondence between GL2 equivalence classes of binary cubic forms and isomorphism classes of cubic rings. So at least in that case, it might be familiar. Okay, so that's the ring associated to a binary form. And the parametrization will concern ideal classes of these rings. And so I need to tell you about the fractional ideals of these rings. So let's consider the R submodule IFK sitting inside KF. Here, K is an index from 0 up to n minus 1. And IFK is going to be a free rank n R submodule with this basis. So 1 theta up to theta to the k, followed by zeta k plus 1 up to zeta n minus 1. Now, it turns out that IFK actually has the structure of RF module. So it's in fact a fractional ideal of RF. And this notation IFK makes sense because IFK is just the kth power of IF1. Another interesting property of IFK is that it is invertible precisely when f is primitive as a binary form, meaning that the GCD of its coefficients is 1. Okay, IFK is what's known as a based fractional ideal of RF because it has a given basis. So if we're given a based fractional ideal I of RF, we define the norm of I to be the determinant of the map, taking the basis of I to the zeta basis of RF. And so it's easy to check that the norm of IFK is just f naught to the minus k, leading coefficient to the minus k. So this construction might also seem somewhat arcane, but it should be familiar in some small examples. So when n equals 2, the map sending a binary quadratic form to the ideal class of IF1 agrees with the well-known bijection between SL2Z classes of binary quadratic forms of discriminant D and elements of the class group of Q adjoint the square root of D. So in that case, it might be a familiar construction. And another important thing to keep in mind is that IFN minus 2 happens to be an explicit representative of the class of the inverse different of the ring RF. That is to say, as RF modules, IFN minus 2 is just RF dual. That will be important for the parametrization. And now I'm in position to tell you about the parametrization. I'll start by discussing a related theorem of Hecke. So let K be a number field with ring of integers OK. We have the following theorem of Hecke, which states that the class of the different in the class group of OK is a perfect square. So this is a celebrated theorem, and it has received no shortage of admiration in the literature. In his textbook, Basic Number Theory, they placed Hecke's result in a dedicated section entitled Coronodus Loco, which is a Latin phrase that roughly translates to crowning moment. And Patterson and Armitage wrote books of Hecke's, they wrote reviews of Hecke's algebraic number theory book, in which they agreed with We's characterization. They thought this was an amazing result. As amazing as it is, the proof of this result is not constructive. It says that there exists a square root of the class of the inverse different, but it doesn't give you a recipe for constructing one. And because of that, Emerton posted the following question on Math Overflow in 2010. He asked, does the ideal class of the different of K have a canonical square root? Can you exhibit a square root of the class of the different? And the answer is yes, in some cases. So when K arises from an even degree binary form, then you can just consider this ideal class here, the ideal class of IF n minus 2 over 2. And that will be, that will square to the inverse different, for example. But otherwise, we don't really have much of a sense of whether you can construct a square root of the class of the inverse different, whether there exists a canonical one, we don't know. So that led to the following question. Even if we cannot always construct a square root of the class of the inverse different, can we somehow still use Hecke's theorem to achieve something? And so in that light, Ellenberg asked the following question as part of the same Math Overflow thread. he asked, is there a parametrization in the sense of Bhargava for cubic rings together with a square root of the class of the different? And the main result of my thesis answers the generalization of Ellenberg's question to rings of any degree n at least 3 that are defined by integral binary n forms. So note that by the Delaunay-Faddeev correspondence, all cubic rings are defined by integral binary cubic forms. And so in particular, we're answering Ellenberg's question in full. Okay, so now let me state the parametrization. So for this, let f be an integral binary form of degree n at least 3 with leading coefficient f naught not equal to 0. And let G be the group SLN if n is odd and SLN plus or minus if n is even. So SLN plus or minus here is just the group of matrices of determinant plus or minus 1. And the parametrization states that if you have a square root of the class of the inverse different of RF, then you can produce a GZ orbit of pairs A comma B of n by n symmetric integer matrices. So this space here, z squared tensored with sim2 z to the n, is just the space of n by n symmetric integer matrices. And the pair A comma B that you produce will have the following property. It'll satisfy this relation. Determinant of xa plus yb is equal to f naught inverse times f of x, f naught y, where G in GZ acts on this pair AB via change of basis. So G times AB is GAG transpose, GBG transpose. Okay, so that's the parametrization. And if you look at this binary form here, you can see that it actually has integral coefficients because we're dividing through by f naught, but we're scaling this y coordinate by f naught. So it has integral coefficients and it's monic. So we call this form the monicized form of f and we denote it by f mod. Okay, so now I want to give you a brief outline of how you construct a pair A comma B from a square root of the class of the inverse different. So let's do that. So for this, let I be a fractional ideal of RF, and suppose there is an invertible element alpha of kf such that I squared is contained in alpha times if n minus 2, and the square of the norm of I is equal to the norm of alpha times f naught to the 2 minus n. So if you look at this norm condition here, you might think that that would force equality here. And that would be true if RF is in fact the ring of integers in KF. But if RF is not the ring of integers, if RF is a non-maximal order within the ring of integers, then having this norm condition doesn't necessarily force equality here. So when I talk about square roots of the class of the inverse different, really what I mean are fractional ideals I satisfying this kind of relation with this norm condition. Okay, so if you're given a pair of a fractional ideal I and a number alpha satisfying these conditions, then we can consider the following symmetric bilinear form on I with values in IFN minus 2. Just takes two numbers beta and gamma in I, multiplies them and divides by alpha, and then you'll get an element of IFN minus 2. So that's a symmetric bilinear form. Now a bit of notation. So I'm going to define two functionals, psi n minus 2 and psi n minus 1 on IFN minus 2. Psi n minus 2 is just going to be projection onto the theta n minus 2 basis vector. And psi n minus 1 is minus a projection onto zeta n minus 1. Okay, so given those functionals, we can compose those functionals with our symmetric bilinear form. And we get two new symmetric bilinear forms on I with values in R this time. And if you choose an R basis of I, then you can represent these two symmetric bilinear forms with n by n symmetric matrices over R. And those are going to be the matrices A and B. Okay, so that's how you get the matrices A and B. And now the group G of R acts via change of basis on I, and that action induces the action that I defined before. G acting on AB is just change of basis on AB. So that's how you get an orbit from a square root of the class of the inverse different. Okay, so that's roughly how the proof of the construction of the parametrization goes. And now you might ask, well, what pairs A comma B actually arise from this parametrization? Which ones show up? So if you have a pair A comma B such that the determinant of xa plus yb is equal to this monosized form f mon of xy, then we show that the GR orbit of AB arises from the parametrization if and only if the following conditions are satisfied. So remember, I defined these polynomials pi before. If you take pi and you evaluate it at the matrix 1 over f naught times minus BA inverse, this matrix here has got to be a matrix with integral entries. That's the condition for the pair A comma B to arise from the parametrization. So it's a bit of a funny condition. The takeaway from that theorem should be that the image of the parametrization is defined by congruence conditions, modulo f naught to the n minus 1. And that's not very good because it seems to suggest that the parametrization depends very heavily on the leading coefficient. If its image is defined by this very large power, it's defined modulo this very large power of the leading coefficient. And for applications concerning binary forms with varying leading coefficient, it would be helpful if the image were defined just mod f naught rather than a higher power of f naught. That would mean that the parametrization doesn't depend too much on the leading coefficient. And so in that regard, together with Bhargava and Shankar, we noticed the following. When RF is the ring of integers of its fraction field, then these complicated looking conditions are actually very simple. They just amount to saying that the matrix B has to have rank at most 1 mod f naught. So if you think of B as being a quadratic form, remember B is a symmetric matrix, so you can think of it as being a quadratic form, then this is just saying that B should be a multiple of the square of a linear form, mod f naught. So it's very, very simple in the case where RF is the ring of integers of a number field. And in that case, the image of the parametrization is defined, mod f naught, not some higher power. Now, in the case where RF is not the ring of integers of a number field, when it's an order within the ring of integers, these conditions are not defined, mod f naught. There's no way to simplify that. But what is true is that these conditions are very closely approximated by conditions that are defined, mod f naught. So if you look at this matrix here, pi of 1 over f naught times minus BA inverse, it turns out that the entries of this matrix are linear combinations of the I by I minors of B. And those linear combinations have denominator equal to f naught to the I minus 1. And so if the I by I minors of B are all divisible by f naught to the I minus 1, if this condition here is satisfied for each I from 2 up to n, then all of these conditions are satisfied, and so the pair A comma B will arise. So these conditions right here, these PI conditions, are very closely approximated by just saying that the I by I minors of B are congruent to 0, mod f naught to the I minus 1 for each I. Now, these minor conditions look like they're defined modulo large powers of f naught, but they're actually not. They're defined mod f naught, because whether or not these minor conditions are satisfied depends only on the residue class of B mod f naught. That's a funny property of these conditions. So the point is that even if the image of the parametrization is not defined mod f naught, it's pretty closely approximated by a locus that is defined mod f naught. That'll be good enough for our applications later. Okay, so now I want to talk about applying the parametrization, and I'll start with the applications concerning binary forms of fixed leading coefficient. And before I do that, I want to explain briefly how we use these parametrizations to prove theorems in arithmetic statistics. So the first step is an algebraic step. We parameterize our arithmetic objects of interest in terms of the integral or rational orbits of a co-regular representation, a group G acting on a vector space V. So a co-regular representation is one where the ring of invariance of the representation is freely and finitely generated. That's all it means. Now, if the arithmetic objects of interest correspond to rational orbits, then we check that these orbits have integral representatives. As an example of what a co-regular representation is, V could be, say, the space of binary quartic forms, G could be the group PGL2, PGL2 would act on V via linear change of variable, and then the ring of invariance of that action is going to be freely generated by two homogeneous polynomials, I and J of respective degrees 2 and 3. So that's an example of a co-regular representation. And once you've achieved this algebraic step, you've turned the problem of counting the arithmetic objects of interest into a problem of counting integral orbits of the co-regular representation. And the way we count integral orbits of a co-regular representation is to realize these integral orbits as lattice points in a fundamental domain for the representation. And once you've done that, you can just use geometry of numbers methods and sieve techniques to count those integral representatives. So that's the strategy we'll be using. Okay, so now I'm ready to talk about the first application of the parametrization, which is to studying two torsion in the class groups of rings defined by binary forms. So in the case where Rf is the ring of integers of its fraction field Kf, then Hecke's theorem tells us that there exists a square root of the class of the inverse different. Now the set of such square roots forms a torsor for the two torsion in the class group. And so in particular, if you want to count two torsion elements in the class group, it suffices to count square roots of the class of the inverse different. And so using the parametrization together with the counting strategy, we get the following result. So let n be odd, let f naught be a non-zero integer, and suppose we factor f naught as m squared times k, where k is a square free number. This will be a unique factorization of this form. Then when number fields arising from integral binary n-ic forms f with leading coefficient f naught, with R1 real roots and R2 pairs of complex conjugate roots are ordered by height, the average size of the two torsion in the class group is at most the following: 1 plus 2 to the 1 minus R1 minus R2, plus this additional term here, which is 2 to the 1 minus R1 minus R2 times a factor that depends on the leading coefficient. So this factor is 1 divided by the sum of divisors of k times k to the n minus 3 over 2. And I have an less than or equal to star here. The star means that this upper bound is expected to be optimal. That is to say, we conjectured that there should be equality here. Okay, so this theorem was previously proven in the case where n equals 3, the cubic case by Bhargava, Henke, and Shankar. And in the case where the leading coefficient is 1, the monogenic case by Siad. And so I've stated this theorem in the case where n is odd, so we're looking at odd degree number fields, but there's a perfectly good analog of the theorem in the case where n is even. It's just too hard to state, so I'm not going to state it here. Okay. So why have I put this term in red here? The reason is that if you look at the Cohen-Lenstra heuristics, which were subsequently updated by Cohen and Martinet and also by Mala, they predict that when you range over all degree n Sn number fields K, with R1 real embeddings and R2 pairs of complex conjugate embeddings, the average size of the two torsion in the class group should just be 1 plus 2 to the 1 minus R1 minus R2. That's this first term right here. But what we notice is that when we look at rings defined by binary forms and we fix the leading coefficient, we're getting this surprising dependence on the leading coefficient. That was not really expected. But it's not such a big deviation from the Cohen-Lenstra heuristics, because if you take this red term and you average it over all leading coefficients, you'll get 0. And so when you range over all leading coefficients, this extra term vanishes and you get a result that agrees with the Cohen-Lenstra heuristics. So somehow fixing the leading coefficient affects the Cohen-Lenstra model, and we don't quite know how that works. Okay. So I'm now going to move on to the next application. So this application concerns superelliptic equations. So let f be an integral binary form that's separable of odd degree n, at least 5. I'm going to write n as 2n plus 1. Now, if you look at the equation z squared equals f of xy, that's called a superelliptic equation. And it's not very interesting to study the rational solutions to this equation. The reason is that if you take any two rational numbers, x naught and y naught, you can just set z naught to be f of x naught, y naught. And then z naught to the big N plus 1 squared will be equal to f of x naught z naught, y naught z naught. So you get...
Could I just ask a brief question about the previous result?
Yes, absolutely.
So here, how serious is there's some hypothesis, isn't here, about your fields? You're looking at rings that are represented by an integral binary n-ic form. Is that right? So yes. What kind of a restriction is that?
Yeah, so
Meaning,
in the case of cubic fields, every
right,
cubic
it's
field
okay.
will come.
Yep.
But the moment that you get to quartic fields, we expect that 0% of quartic fields come from binary forms. And so this is actually quite a thin family. But as I said, when you average over all leading coefficients, this red term vanishes. And so we get a result that agrees with the Cohen-Lenstra heuristics, which says that even when you're looking at this extremely thin family of number fields coming from binary forms, the Cohen-Lenstra heuristics still seem to apply.
Yeah, at least for this two part of the class group. And
that's right.
When you say it's thin, like is it like root x? I mean, or is it like how thin?
Yeah. So so if the number of quartic fields up to x is x, then the number of binary quartic forms grows with x to the 5/6.
Okay.
So yeah.
Okay. Good. Thank you.
Yeah. Okay. Great. So yeah, I was talking about these superelliptic equations and their rational solutions. So yeah, so if you have two rational numbers, x naught, y naught, you can set z naught to be f of x naught, y naught. And then you can produce a rational solution to the superelliptic equation just by scaling x naught and y naught by z naught. Okay. So rational solutions to these equations are kind of trivial, and you can express this triviality geometrically as follows. So you look at the vanishing locus of z squared minus f of xy. That naturally lives inside this weighted projective plane where x and y have weights 2 and z has weight 2n plus 1. Now this weighted projective plane maps down to P1, where you forget the z coordinate. And you consider the composition here, you get an isomorphism of this vanishing locus with P1. So basically, over the rational numbers, this equation is just P1. It's not very interesting. Now, if you consider, however, primitive integer solutions, that is pairs x naught and y naught of integers such that the GCD is equal to 1, well, then you can't do the scaling trick because that would violate the GCD condition. And so it turns out to be very interesting to look at primitive integer solutions to this equation. And in that context, we have the following analog of Falting's theorem, which was proven by Darmon and Granville in 1995. They showed that if you look at the equation z squared equals f of xy, then that has finitely many primitive integer solutions. And so given that each of these equations has finitely many primitive integer solutions, we might expect that most of them have no solutions at all. And that's what we can use the parametrization to prove. So it turns out that if you have a primitive integer solution to this equation, then you can actually construct from that solution a fractional ideal of Rf, whose ideal class is a square root of the class of the inverse different. So primitive integer solutions give rise to the input to the parametrization. And so therefore they give rise to integral orbits of a representation, and we can count them. And that yields the following result. So let's fix an odd number f naught that's not a perfect square. And let's factor again f naught as m squared k, where k is square free. Then for all sufficiently large odd degrees n, a positive proportion of degree n forms f with fixed leading coefficient f naught are such that z squared equals f of xy, the superelliptic equation, has no primitive integer solutions. More specifically, we'll define the quantity mu f naught to be the product over primes dividing k of this small quantity here, p to the minus 2 plus p minus 1 times p to the minus big N minus 1. Then we show that the density of forms f such that z squared equals f of xy has a solution is bounded above by mu f naught plus little o of 2 to the minus big N. Furthermore, we show that a positive proportion of degree n forms f with fixed leading coefficient f naught are such that this equation here, z squared equals f of xy, fails the Hasse principle, meaning it has points everywhere locally, but doesn't have a point globally, and it fails the Hasse principle due to a Brouwer-Riemannian obstruction. So to give you a sense of how strong the theorem is, suppose that the set of primes p dividing k contains just 2, 3, and 7. Then what is the density of insoluble equations predicted by the theorem? Well, that's 1 minus this density of soluble equations. So that would be 1 minus mu f naught plus little o of 2 to the minus n. Now, as the degree gets big, you take the limit as n goes to infinity of this quantity, what you'll get is something more than 99.9%. So as soon as this number k has a few prime factors, we're saying that most of these equations have no solutions. So you could think of this as saying that most odd degree binary forms don't primitively represent a square. Okay, so that's the second application. And now I'm ready to talk about the third one. This concerns two Selmer groups of hyperelliptic Jacobians. So in this case, f is going to be a separable form of even degree, n at least 4. And we can look at the curve z squared equals f of xy. It's a hyperelliptic curve. We denote it by cf. And we'll call this.
Sorry, Ashvin. Sorry,
yeah.
to interrupt again. So go back to the previous thing.
Yeah.
So what happens is mu only depends on the prime divisors of k, right?
That's right.
So when you say what goes to infinity, the number of prime divisors goes to infinity, or what? Maybe that's what you meant.
Yeah.
The number of prime divisors.
Right. So,
okay. Got it. Okay.
Yeah, I'm sending the degree to infinity. I'm just saying you just need three primes dividing k, and you're already at 99.9% have no solutions.
But why will, mu only depends on the prime divisor. So it's
Sorry, mu also depends on the degree. There's this.
Yes. But you've got this 1 over p squared term, no?
That's right. Yeah, I mean, this degree dependence is not very meaningful, but the reason I'm sending n to infinity is really to take care of this little o. Little o to the minus n.
Okay.
Yeah. Okay. Right. Okay, yeah, so we're looking at these hyperelliptic curves, z squared equals f of xy, denoting the Jacobian j of cf. Now I want to define the notion of two-Selmer group. I'll give a very brief definition. So a two cover of the curve CF is just a cover of CF, where the automorphism group of the covering is isomorphic to the two torsion of J of CF as a Galois module. And similarly, you can define a notion of two cover of J of CF. Okay. We'll say that a variety over Q is soluble if it has a rational point, and locally soluble if it has rational points everywhere locally. And then the two-Selmer group, which we denote by cell2 JCF, as a set is just locally soluble two covers of J of CF. That's what it is as a set. And it's been a long-standing objective in arithmetic statistics to parametrize and count two-Selmer groups of Jacobians of hyperelliptic curves. So let me tell you how this goes. So to warm up, let's consider the case where we're working with families of hyperelliptic curves that have rational points, say a family of curves with a marked point. So in that case, the curve CF will embed into its Jacobian via the Abel-Jacobi map, and pullback via this map induces a bijection between locally soluble two covers of J of CF and locally soluble two covers of CF. So if you want to count the two-Selmer group of J of CF, you can just count these locally soluble two covers of CF. And in that regard, we have the following theorem of Bhargava, which he proved using Wood's thesis. He showed that if you have a locally soluble two cover of CF, then you can produce a pair A comma B of symmetric n by n integer matrices such that the determinant of xa plus yb equals f of xy. And the pair A comma B that you get is sort of only unique up to the action of this group SLN mod mu2 of Z. So this theorem has been used to great effect in the literature. It's been used to determine the average size of the two Selmer groups in families of hyperelliptic curves with marked rational points. For example, in the families of monic hyperelliptic curves. You might know these papers of Bhargava Gross and Shankar Wang that achieve this. But there's a serious problem, which is that if your hyperelliptic curves don't necessarily have rational points, then you can't apply this theorem. The reason is that this right-hand side may be empty. There may not exist a pair A comma B with determinant xa plus yb equals f of xy when the curve CF does not have a rational point. So for that very serious looking problem, we have quite a silly solution. We just manufacture a rational point. By taking the binary form f, and we replace it with the monetization F mod. So the curve CF mon is a monic hyperelliptic curve. Therefore, it has a rational point. And it's just a twist of CF by the at most quadratic extension Q adjoin the square root of F naught. Now it's easy to see that the two torsion of the Jacobian of CF is isomorphic to the two torsion of the Jacobian of CF mon. And that identification induces an identification on their H1s. And this identification of H1s takes the two Selmer group of J of CF, which lives in here, and it sends it to certain two covers of the Jacobian of CF mod. It doesn't map it to the two Selmer group necessarily of the Jacobian of CF mod, but it maps it to some set of two covers. And what we will do is we will parametrize the image of the two Selmer group of J of CF in this H1 here. So now I need to make a technical assumption. If 4 divides the degree, that is, if the genus of our curves is odd, I need to assume that the curves under consideration have rational points everywhere locally. That's just a technical assumption. Okay. Then it turns out that if you have an element of cell 2 of J of CF, we can construct a square root of the class of the inverse different of RF. Again, that's the input to the parametrization. So combining it with the parametrization, we find that the two Selmer group of the Jacobian of CF naturally maps into the set of pairs A comma B of n by n symmetric integer matrices such that the determinant of xa plus yb is equal to F mod rather than F of xy. And again, the relevant group action is SLN mod mu2 of z. Okay, so with that parametrization in hand, using the counting strategy, we get the following theorem. This is joint with Bargava and Shankar. We prove that if you look at binary forms F over Z of even degree n at least 4 with fixed non-zero leading coefficient F naught, under the technical assumption that the curves are locally soluble if the genus is odd, then the average size of the two Selmer group of the Jacobian is at most 6, and we expect that there should in fact be equality here. Okay, so 2 remarks about this theorem. The first is that it is robust under the imposition of any finite set, or even very general infinite sets of congruence conditions. So you can look at families of binary forms defined by congruence conditions, and this bound of 6 will remain. And the second remark concerns the Poon and Raines conjectures. So they have conjectured the distribution of the Selmer groups of even genus hyperelliptic curves. And they conjecture that the average size should be 6, so this confirms that conjecture. But it also goes a step further by saying that even in the odd genus case, under this locally soluble technical assumption, we still get a bound of 6. Okay, so that summarizes the applications to families of binary forms with fixed leading coefficient. Now I want to talk about varying the leading coefficient. So the goal here is to say, compute the average size of the two Selmer group of J of CF over all binary forms F under this technical assumption. And naively, you might think, okay, let's just get an asymptotic count of the Selmer elements for each fixed leading coefficient and simply sum those asymptotics over all leading coefficients. So let's try to do that. So given a non-zero leading coefficient F naught, let SF naught of X be the set of binary forms where the height is less than X and the leading coefficient is F naught. Now the height function that we use for binary forms of fixed leading coefficient is defined as follows. It's H star of F, and it's the maximum over all I of F naught to the I minus 1 times Fi raised to the 1 over I. This turns out to be the natural height function for binary forms with fixed leading coefficient. And then the theorem that I mentioned 2 slides ago with Bargava and Shankar about the average size of the two Selmer group of the Jacobian can be restated as follows. It says that the sum over all forms F in SF naught of X of the size of the two Selmer group of J of CF is less than this factor depending on F naught times X to the n times n plus 1 over 2 plus some negligible error term. Now, there's a problem, which is that if we're trying to vary the leading coefficient, well, you look at this height function. It depends on the leading coefficient in a terrible way. So that looks really bad. We would like to use a more natural height on binary forms. For example, we would like to use the height function that's just the maximum of the coefficients. Now that poses a problem because if you look at this set SF0 of x using this funny height function, that's very different from the set of binary forms f whose height h of f is less than x with leading coefficient f0. These two sets are generally not the same, unless f0 is roughly the size of x. If f0 is roughly the size of x, then h star and h are pretty close to each other. And so these two sets will agree there. And it turns out that when you're varying over leading coefficients, you don't need to consider the case where f0 is not the size of x. When f0 is smaller than x, that gives a negligible contribution. So most of the time, we can just replace this complicated height function with this very simple height function. Okay, that's the first step. So now we can just take this bound here on the right-hand side and sum it over all leading coefficients. If we do that, and if we ignore the error term, we find that the average size of the two-Selmer group of the Jacobian over all binary forms is 1 divided by the number of binary forms of height up to x times the sum over f0 roughly the size of x of the bound. And if you approximate the sum with an integral, you'll find this is x to the n plus 1. And this denominator here is also x to the n plus 1. And so we get 1. So this proves, ignoring the error term, that the average size of the two-Selmer group of the Jacobian is bounded over all binary forms. Now, the problem is that when the leading coefficient is close to x, which is the range that we are interested in, the error term will overtake the main term if you're not careful. So we need to understand the error term better, and there are multiple sources of the error. And the worst source of the error comes from an application of what's known as Davenport's lemma. So I said that the way we count these Selmer elements is we parametrize them as integral orbits, and then we realize those integral orbits as lattice points in a fundamental set. And then we use geometry of numbers methods to count those lattice points. Well, the geometry of numbers method that we use is known as Davenport's lemma. And it's a basic principle that states that the number of lattice points satisfying congruence conditions in a round-looking region is approximately the volume of the region times the probability that those congruence conditions are satisfied. That's just a general principle in the geometry of numbers. But the problem is that when the modulus of your congruence conditions is roughly the size of the region, which is the case here, the modulus of our congruence conditions depends on f0, and the region has size approximately f0, then Davenport's lemma won't work very well. Okay, so we need to try to understand the error term better, and that will require understanding the parametrization better. So to control the error, we need to understand the image of the parametrization better. So I'm going to recall some things that I mentioned in a previous slide. So recall that a priori, the image of the parametrization was defined by these congruence conditions mod f0 to the n minus 1. If you have a pair AB with the determinant of xa plus yb equals this monicization, then it comes from the parametrization if and only if these funny matrices here have integral entries for each I. So recall that we say a symmetric n by n matrix B has rank at most 1 mod f0. If you view B as a quadratic form, then it is proportional to the square of a linear form, mod f0. And what we had shown was that if the ring RF is the ring of integers of its fraction field, then B is going to have rank at most 1 mod f0. So in that case, the image of the parametrization is defined mod f0, not mod f0 to the n minus 1. We also had the set of conditions here that give a very good approximation to these more complicated conditions. We said that if the I by I minors of B are all divisible by f0 to the I minus 1 for each I from 2 up to n, then the pair A comma B will come from the parametrization. And so now I want to give you a sort of partial converse to the second bullet point. And so far, we only know how to prove this converse in the case where n equals 4, but we expect it to be true in general. So if you have a pair A comma B that is not defined mod f0, then what you can do is you can translate that pair under the group SL4 mod mu2 of Q. So if you the translate that you get will be A prime, B prime. This will be a pair of integer matrices such that B prime satisfies the conditions in the second bullet point. The I by I minors of B prime will be divisible by f0 to the I minus 1 for each I. And so the implication here is that at least in the quartic case, even if you're getting something from the parameterization that's not defined mod f naught, you can just translate it under this group SL4 mod mu2 and get something that is defined mod f naught. So for all intents and purposes, you can just think of the parameterization as producing orbits that are defined mod f naught. So that's reduced the modulus down from f naught to the n minus 1 to f naught. Okay, so now I want to sort of explain the error coming from Davenport's lemma using diagrams. So roughly speaking, what we want to do is we have a region of side length x, and we want to count lattice points in this region that are defined by congruence conditions modulo a number m. So if m over x is tiny, that's the situation in this first diagram here, then you can see that the lattice points are very nicely equidistributed in the box. And so Davenport's lemma, basic geometry of numbers techniques, will give a very good estimate for the number of points. But remember that the orbits we want to count were defined by conditions mod f naught. And the regime we're interested in is where f naught is roughly the size of x. So that's the situation depicted in the second picture here. The modulus is roughly the size of x. Then it's possible that the points we want to count are very sparsely distributed in the interior and possibly clustered around the edges. And in that case, Davenport's lemma will give a huge error. You won't get a very good estimate for the number of points in this region. So we want to prove that this situation here does not occur. That is to say, we want to show that even when the modulus is roughly the size of x, we're getting equidistribution in the box. And we achieved that using Fourier analysis. I'm not going to get into too much of the details here, but very briefly, let chi be the indicator function mod f naught of the image of the parametrization. Then by Poisson summation, proving that the lattice points coming from the parametrization are somewhat equidistributed amounts to bounding this sum, the sum over b non-zero of the size of the Fourier transform chi hat of b. And it's easy to show if, for example, the leading coefficient is a prime p, you can use the theory of exponential sums to show that the size of chi hat of b is bounded by p to the 4 minus half the rank of b. And this power saving here of half the rank of b will be enough to get a sufficient bound on this sum, and hence enough to prove that the points coming from the parametrization are somewhat equidistributed. The takeaway here should be that proving this kind of equidistribution result is just a bit of Fourier analysis. Okay, so once you've shown that the points coming from the parametrization are equidistributed, we get the following theorem. We can vary over leading coefficients, so we can prove that when integral binary quartic forms f, such that CF satisfies this technical condition that it's locally soluble, are ordered by the max norm on their coefficients, the average size of the two Selmer group is at most 6, and we expect equality. Now, if you look at this family of curves CF, where f ranges over all binary quartic forms, there's a lot of redundancies in there. Because if f and f prime are, say, PGL2Q equivalent binary quartic forms, then CF and CF prime are isomorphic. So ideally, what we would want to do is quotient the family of binary quartic forms by this PGL2Q action and prove the theorem on that quotient family. And we're actually able to do that. So crucially, the average remains at most 6 with expected equality, even if we quotient the family of binary quartic forms by the action of PGL2Q. Okay. So as a consequence of that, we're able to study higher moments. So now I want to talk about the second moment of the size of the two Selmer group of elliptic curves. Before I do that, I want to give some background on elliptic curves and their Selmer groups. So recall that every elliptic curve over Q is isomorphic to a unique curve of the form EIJ with equation y squared equals x cubed plus ix plus j, where I and j are integers such that if p to the 4 divides I, then p to the 6 does not divide j. And we order elliptic curves by height, so h of EIJ is just the max of 4i cubed and 27j squared. So the question we're interested in is, what is the distribution of the two Selmer group of E as E ranges through all elliptic curves ordered by height? And Poonen and Raines have a conjecture for what this distribution should be. And regarding the moments of the distribution, they make the following beautiful prediction. The mth moment of the two Selmer group of E should just be the product I goes from 1 up to m of 2 to the I plus 1. So for example, the average should be 3, and the second moment should be 15. So I would say that very little progress has been made towards proving this conjecture. In fact, until recently, the only case that we knew was the case of the first moment, the average. Bargov and Shunker famously proved that the average size of the two-Selmer group is equal to 3. I want to briefly talk about their proof. It proceeds by means of the same parametrize-and-count strategy. And the representation that they use is this representation of binary quartic forms with a PGL2Q action that has two invariants I and j of degrees 2 and 3. And the parametrization that they use is due to Birch and Swaminathan-Dyer. So Birch and Swaminathan-Dyer proved that the map taking a binary quartic form to the corresponding genus 1 curve CF defines a bijection between the set of PGL2Q orbits of binary quartic forms with integer coefficients that have invariants I and j, such that the curve CF is either soluble or locally soluble. So it defines a bijection between those binary quartic forms and the set of isomorphism classes of either soluble or locally soluble two covers of Bij. So the takeaway here should be that two Selmer elements of elliptic curves correspond to binary quartic forms. So now in what follows, I'm going to abuse notation slightly by writing F in the two Selmer group of E to denote the corresponding binary quartic form. Okay, so that's the case of the average. And now, together with Bargov and Shunker, using the new parametrization, we're able to make this progress toward studying the second moment. So we're able to show that the second moment is at most 15, and of course, we expect equality to be true here. So how do we prove this? Well, we want to count pairs f and f prime of two Selmer elements of elliptic curves, and we do that by fibering over the first factor. So let's fix a two Selmer element f of an elliptic curve E, and let's consider the following two cases. The first case is that f is the identity element. Now, every elliptic curve has an identity two Selmer element. So f being the identity element doesn't really impose any conditions on our elliptic curve. And the Poonen-Raines heuristic suggests that there should be three choices for f prime on average. And remember, that was proven by Bargov and Shunker, that you should have three two Selmer elements on average. So in the case where f is the identity, the number of choices for the pair f prime on average is 3. Now in the case where f is not the identity, the Poonen-Raines heuristic says that there should be two choices for f, 3 minus 1 choices for f on average. And once you've fixed that non-trivial two Selmer element f, the elliptic curve E has a marked non-trivial two Selmer element, namely the one corresponding to f. And we expect that this marked non-trivial two Selmer element will cause the two Selmer group to double in size. And so we expect that there should be 6 choices for f prime on average in this case. So how do we prove that? Well, the two Selmer group of E is just isomorphic to the two Selmer group of the Jacobian of CF. And remember that we computed the average size of the two Selmer group of the Jacobian of CF. So the average number of choices for f prime is just the average size of this two Selmer group, where we're working with binary quartic forms f up to the PGL2Q action. And we showed that that average size was at most 6. So combining cases 1 and 2, we get that there's 1 times 3 plus 2 times 6, making for a total of 15 choices for f prime on average. And so that gives this bound of 15. So that's how we get the second moment. And I want to finish the talk by discussing a related second moment. So let f be an integral binary cubic form with leading coefficient 1, monic, such that the ring RF is in fact the ring of integers of its fraction field. So in this case, KF is going to be a monogenic cubic field. The reason is that its ring of integers is singly generated. It's generated by the root of f. So as I mentioned, there is a close connection between two torsion and the class groups of these monogenic cubic fields and two Selmer groups of elliptic curves. And so you can use class field theory to show that if you look at the dual of the two class group of this ring RF, and that actually corresponds to binary quartic forms. And those binary quartic forms correspond to two Selmer elements of the elliptic curve y squared equals f of x comma 1 via the parametrization of Birch and Swaminathan-Dyer. So you can embed the dual of the two class group in this two Selmer group of this elliptic curve. And the same method that we use to get the second moment of this two-Selmer group will work for this subset corresponding to the dual of the two-class group. And so we get the following theorem. When fields arising from monic integral binary cubic forms F with either 3 or 1 real roots are ordered by height, the average size of the second moment of the two-class group of RF is at most 3 or 6. And again, we expect equality. So now I have a table to summarize sort of the results about the two torsion and the class group of these monogenic cubic fields. So this family of fields arising from monic integral binary cubic forms, remember, we had a theorem previously giving the average size of this. So when the number of real roots is 3, we got that the average was 3/2. And now we're saying that the second moment is 3. And if you compare that, these numbers in blue are the Cohen-Lenstra heuristics, the predictions of the Cohen-Lenstra heuristics. So the Cohen-Lenstra heuristics predict that when you range over all cubic fields, you should get an average of 5/4. So this 3/2 is bigger than 5/4, meaning that fixing the leading coefficient to be 1 causes an increase relative to Cohen-Lenstra. And here, the Cohen-Lenstra heuristics predict 15/8, and we're getting a second moment of 3. And so 3 is bigger than that. So again, we're seeing this increasing effect on the second moment. And when there's 1 real root, so complex cubic fields, we're getting an average of 2 when the prediction is 3/2, and we get a second moment of 6 when the prediction is 3. So fixing the leading coefficient affects not just the first moment, but also the second moment. Okay. That concludes the talk. Thanks so much for coming, and thanks for this opportunity.